This is River Wu from Chiba University, Japan. Firstly, thanks to the committee to give the Dr. Xiaolong Lo this chance to give the presentation, but due to the visa problem, he cannot go to the Japan for give his presentation. So instead of him, I got the slide and contents 2 days ago, and to give the presentation for him. His presentation, his research is about proposing an improved technique to optimize freehand selection in interaction with distant large displays in terms of selection efficiency, accuracy, and user experience. So maybe during my presentation you will have some questions to ask. Maybe I cannot answer you directly, so please not hesitate to contact him via email. I'd like to introduce the author. He is called Xiaolong Lo, and he's a PhD candidate from Zhejiang University, China. And his main research is about motion sensing human-computer interaction, ubiquitous computing in large displays, interaction design and evaluation methodology, and collaborative interaction, and user experience research and design. This presentation is organized as 6 parts. Firstly, we describe the background of the research, then about the objective of his work. Thirdly, we put forward the context and depict the implementation of his optimizing technique. To evaluate the new technique, he designed an experiment and conduct. Firstly, we present the analysis and results of the experiment. Then we summarized the findings and the implications based on the results and draw some conclusion and future work. This is the first part about the background of the research. Compared to the mouse-based touching interactions, freehand interaction has more flexibilities in interaction position and distance, especially in circumstances of large displays. These flexibilities allow users to freely change their interaction locations. In this regard, freehand interaction is a more suitable interaction method in context of large displays. But there still have some usability issues that are concerned in freehand interaction with large displays. First, large displays have far larger physical area than users' visual fields and users' reachable area by traditional interaction method. Thus, those distal objects on large-scale user interfaces are more difficult to be perceived and reached. These limitations cause efficiency problems of interaction on large displays. Second, freehand movements in mid-air has a lower accuracy than mouse movements, and tracking of users' hand movements has a limited recognition accuracy of motion sensing cameras. This accuracy problem is another limitation of freehand interaction on large displays. To address the efficiency and accuracy problems, technologies and techniques proposed in earlier research are mainly 3 types: the dual precision techniques, and the pointer acceleration, and features applied on target and the cursor. The dual precision and precision techniques refers to 2 precision modes: the coarse mode and the precise mode. Users use the coarse mode for quickly approaching the target, while the precise mode for precisely focusing on the target. Another kind of technique, the pointer acceleration, adapts the cursor's moving speed based on the input side's moving speed. For example, when users move their interaction hands fast, the cursor's movement is transferred to a large moving speed by a large cursor to display gain. But when users move hands slowly, the cursor's movement becomes more fine-grained. The other techniques developed special features such as SIGCHI and gravity to make targets more easily to be pointed by the cursor, or to make the cursor more easily touch the adjacent targets. Regardless of the preceding method, users' physical movements in front of large displays are less considered in their effects and potentials on optimizing freehand interaction performance. These two issues are of great significance to reveal the advantages and disadvantages of users' physical movements in freehand interaction with large displays. Thus can imply valuable suggestions for the future design of the freehand interaction techniques and the user interfaces in large display environments. The design concept of the optimizing technique is based on the observation that users spontaneously move left hand and right hand to reach the digital information on large displays. While they step closer to or farther away from the large displays to switch between overall and local views of user interface, the user's movement in left and right directions is defined as horizontal navigations, while movement in distance is defined as interaction distance change. In this paper, users' horizontal navigations are automatically tracked to optimize interaction efficiency. Users' distance changes are adapted to adjust the freehand selection accuracy. Given the new selection technique, we conduct an experiment to evaluate the new technique. Because the pointer acceleration technique is the most frequently used selection method in most interaction systems, thus it is selected as the baseline technique in this study. The new optimizing technique is developed on the basis of PA technique. In this study, we implemented the baseline technique based on CNR method. The moving speed of cursor is calculated by multiplying the hand's moving speed by a dynamic cursor to display gain. We call it CD. The dynamic CD gain is calculated based on the hand's moving speed. The faster hand speed, the larger CD gain. The CD gain ranges from 0.2 to 12.2. The correlation between hand speed and the CD gain is illustrated as the figure in this slide. On the basis of PA technique, the new technique captures users' bodily movements in horizontal direction to optimize cursor's movement in horizontal direction. For example, when user move towards left to select the target on the left side of display, an increment is added to the cursor's speed. As the first equation illustrates, in distance adaptation, a dynamic scale factor is multiplied to the cursor's speed to realize different selection precisions. A distance of 2,000 millimeters is defined as the middle distance. When users stand at a distance closer than 2,000 millimeters, a scale factor smaller than 1 point is multiplied. But when users interact at a distance larger than 2,000 millimeters, the scale factor becomes larger than 1 point. The overall calculation equation of cursor's moving speed in the new technology in the new technique is illustrated as equation 2 and equation 3. Then in this part, we describe the details of the evaluation experiment. This figure explains the user interface of selection tasks. On the beginning of each selection trial, an unfilled is shown as a random location at the start circle. Users move the cursor to touch the start circle. Once the start circle is touched, it disappears and another black filled circle shows as the target. The target and the start circle is symmetric from the display center. The distance between the start circle and target is moving amplitude. Target diameter is defined as the target size. When users move the cursor to the target, they need to keep the cursor hovering within the target area 500 milliseconds. If the cursor moves away from the target without sustaining 500 milliseconds, one selection error is recorded. No more than one selection error is recorded in each selection trial. There are two quantitative metrics in this study: movement time, and it refers to the interval from target showing the target is touched by cursor, and another is selection error time for each target location. 3 target size conditions and 2 moving amplitude conditions are designed to build the varied selection difficulties. All participants use 2 selection techniques, respectively, complete 6 selection blocks. Note that after completing 6 blocks for each technique, participants were required to complete 1 questionnaire to evaluate the selection technique, and they were encouraged to give comments on 2 techniques. Total 12 volunteers were recruited as the participants in this study with a mean age of 24.5. 5 of them are females. All participants have normal or corrected to normal eyesight without body impairment. The figure in this slide shows the study scenario. We used the multi-way analysis of variance to conduct the significance analysis, and we used the Turkey SD post-hoc tests for pairwise comparisons. Firstly, compare the movement time between the new selection technique and the baseline technique, and found that there is a significant effect on movement time for techniques. The new physical movement adapted technique has obviously decreased the movement time than the baseline technique. Through the interaction effects analysis, we also found that there have significant interaction effects between technique and amplitude factors. Between techniques and the target size factors, as the pictures revealed, the new techniques has more obvious advantages on movement time in larger amplitude and larger target size conditions. Then we analyzed the selection error rate result of 2 techniques. Overall, the new techniques has a far lower selection error rate than the baseline PA technique. This picture shows the interaction effects between technique and the target size factor. The results show that the new technique has more obvious advantages on selection accuracy in smaller targets. By post-block questionnaire, we measured users' subjective evaluations on the new selection technique and the baseline technique. In terms of 6 user experience metrics, these metrics are mental effort, accuracy, speed, perceived fatigue, comfort, and overall easiness. This bar diagram shows the questionnaire evaluation results on 2 techniques. We can find that the new selection technique was more highly evaluated than the baseline technique in accuracy and efficiency. But in other 4 metrics, 2 techniques achieved almost equal scores. These results indicate that the efficiency and accuracy adaptations of the new technique can be perceived by participants, and the new technique has no effect on operate complexity and easiness compared to the baseline technique. These are 2 cases of participants' comments on the selection techniques. One participant reported that physical movements-based adaptation makes it faster to get the distal targets on the large displays. Another participant told the adaptation in interaction distance was advantageous in both selection efficiency and accuracy. Given the preceding result, we summarized the findings as follows, such as the new physical movement adapted techniques have an optimizing effect on both selection efficiency and accuracy. And the adaptations in the new technique can be perceived by users, and the new technique is preferred to the baseline technique by users. And this is the conclusion part. In addition, we conclude implications from the experiment results. For example, the new technique, there is a contradiction between the efficiency and accuracy optimization. In particular, when selecting the small target, users spontaneous close to the display, which has a benefit on input accuracy, but a negative influence on moving amplitude. Limitations are also noted in this study. For example, a 70-inch flat screen is used as the large display in the experiment. Freehand selection performance on larger displays, such as the wall size screens, is still not investigated. And in addition, the adaptation algorithm adopted in the techniques are quite simple. More suitable adaptation methods are explored in the future work. And finally, we suspect the user's more behavioral dynamics, such as head orientation and manual operation features, can be utilized to promote the selection results in freehand interaction with large displays. And but their potentials are still unclear in currently study. In a summary, this paper proposed a user's physical movement adapted techniques to improve the freehand selection performance in interaction with large displays. The new techniques optimizing effect on selection efficiency and accuracy are demonstrated in this study. The more difficult selection tasks, the more obvious advantages of the technique can get. Furthermore, this new technique relies on users' spontaneous motions in freehand interaction in front of the large displays. Thus, it has equal operate complexities and easiness compared to the baseline selection technique, but its optimizing effects are perceived by users and satisfied by users. So, aforementioned is the research about Dr. Candidate Xiaolong Low's research. If you have some questions, you can contact him via the email on the slide. Thank you so much.
Okay, thanks, River. So I guess as requested, if you have any questions, please forward those on to the author of the paper. And so this is our final presenter for the session. So the good news is that we are a little bit early for coffee, so you get to drink some extra coffee. And